Hello, my name is Tyson Fries and I'm going to explain Huffman encoding. The first thing to know about Huffman encoding is it's a compression algorithm. We're trying to reduce the memory required to store data without losing any of the information. So here on the left, as an example, is some text. And with Huffman encoding, we're going to store that text in less zeros and ones than we were before. And I'm going to show you how that works. The algorithm has really kind of two parts. The first part is the preparation part. Before we do any encoding and decoding, we need to prepare in order to do that efficiently. And then we encode and decode the text. Uh, the way we do it and are able to store information with less bits is by analyzing the data beforehand. We want to see how frequently different symbols appear and then assign those symbols bit strings that are the smallest. So that way, when they repeat, we use the smallest bit strings most often. To do that, we first need to profile the text. It's hard to know which codes to assign to what symbols if we don't know how often the symbols appear. So this is just an example, and I'll walk through the code more in a bit. But first, we just scan the text and see how often every symbol appears. Then we build what's called a Huffman tree. That's done using a priority queue to build the binary tree because we want the symbols that appear most often to have the smallest codes, the smallest Huffman codes, which means they'll be further up the tree. And you'll see more of that as we go. So these priorities here in the queue help us to make sure that symbols that appear the most, like E, A, and the space character in this example, they appear at the top of the tree and are going to have smaller codes as a result. The final step in preparing to encode and decode is to create an encoding map, which we do by traversing the tree. And every time we move left on the tree, we represent that with a 0. And every time we move right on the tree, we represent that with a 1, which then gives us an efficient map for storing these symbols and compressing them. So as an example, we start at the top of the tree and we move left, so that's a 0. And we move left again, so that's another 0. And once we reach E, that's another left, that's a 0. So the code, the Huffman code for this symbol, the E, is going to be 0, 0, 0. And when we go to compress, we'll convert all the E's to 0, 0, 0. If we're going to continue traversing the tree to get the rest of the Huffman codes, we'll move right now, and that's a 1. And then we move left again for the N, and that is a 0. So for the N, the Huffman code is 0, 0, 1, 0. And this continues. We traverse the whole tree and we get Huffman codes for each of these symbols based on whether we move left or right in the tree and mark a 0 or a 1. Once we have that map, we throw it all in a dictionary like this, where E is 0, 0, 0 and N is, like we said, 0, 0, 1, 0. And now we're prepared. And with that preparation, we can now encode and decode with a worst case scenario of O of N, where we just linearly move through each of the elements in the text and can encode and decode quickly. So, as an example, a neat example, we're going to use the word neat. And to encode this word, we first look at the first letter, N, and then move it through the map. And so N, we said, has a Huffman code of 0010. So we will chug that over. And that's what the compressed version of N is 0010. We can do that again. The next letter is E, which, moving through the map, has a Huffman code of 000. And now we've compressed the N and the E as this string on the right of bits. And we continue for all the other letters in the word. And eventually we have this bit string, which is compressed. And I know what you're thinking. Maybe, how is that any smaller than just writing NEAT? Well, N in the computer requires a fixed length of bits, but instead of using these Huffman codes, we're on average going to use smaller bits. And we're definitely going to use a smaller amount of bits to represent symbols that appear most frequently, which is going to make the entire text compressed better. To decode, we use our tree, and we start with the zeros and ones. So we begin. A 0, as we recall, was a left. So we start at the top and move left down the tree. And then we move left again for another 0. And we move right for a 1. And then we move left again for a 0. And now we've reached a leaf node on the tree, which means that this character was an N. And so we mark that out as having decoded the letter N. And then we start again at the top of the tree with a 0, a 0, a 0. And now we've got an E. And you can see we're recreating the word neat from our bit string that we created. And we continue like this until we've got the whole word. So now I want to take you through the code for a walkthrough and a demonstration of how everything works. This is the Huffman tree class that we're using. And within that class is nodes. And each node on the tree represents one of these, and some of them have letters and some of them do not. So let's get into it. First, let's start with a demonstration. So you can see here we've got some text. The rain in Spain stays mainly in the plain. First thing we got to do is see how frequently things appear. And so we profile the text, and then we build that Huffman tree, and then create an encoding map from that tree. So that way we can encode with worst case efficiency of O of n, and decode again with with an efficiency of O of n. So we've got that map, and we use the map that we create and the text. We encode it using that map. And here we have a little test. We're asserting that it is equal to this bit string, because that's the accurately encoded string. And then we're going to take what we've encoded and decode it using our tree, just like we showed in the diagram. And that's going to get us the decoded text. And that decoded text should be equal to what we had at the start. And if that's all true, then we passed. And so let's go ahead and see that in action to make sure our code is working. So we're going to go ahead and run that test, and we've passed, which is awesome. So let's take a look at the code and just see a little more in detail how we are getting that to work here. So I've already showed you this part. Let me talk to you now about what the profiling function does. Profiling the text is going to start just by creating a dictionary to track for each character in the text, or for each symbol, how many times it occurs, which is an integer. So for each character in the text, we're going to loop through it, and if our dictionary contains that symbol already, then we're going to add 1 to increase the number of times that it occurs. And if it doesn't exist yet in our dictionary, then we're going to add it to the dictionary and initialize it with a counter of 1, because we've seen it one time. And then we'll return that profile, so that way we know how frequently everything occurs in the text that we're trying to encode and decode. Well, the next step, in order to prepare to encode and decode with a worst case of O of n, is to build a Huffman tree. We take as a parameter that profile from earlier, and we use that profile to create our tree. So our binary tree, our Huffman tree, is going to start with a priority queue. So that way we know where in the tree things should land. We're going to create a node for each character in our profile. These are the character frequencies in the profile. And so for each of those, we're going to create a new node for that character. And then we're going to insert into the priority queue that node, Z, and its priority in the queue is going to be whatever its frequency was, because if it appears more frequently, we want it to have the shortest Huffman code possible, so as to have the best compression we can. Then we're going to loop through all of the nodes but 1 and combine those nodes according to the highest frequencies. This is building up the top of the tree. Right now we have all of our leaf nodes, and we need the zeros and the ones, the moving left and the moving right within the tree, so that we can encode and decode. So to do that, we take uh, the highest frequency nodes, the two highest frequency nodes, which we're going to call X and Y, and we're going to create a new node to connect them. And that node is going to have the count, the frequency of each of those characters combined as its count. And then we're going to set each of the X and the Y nodes as its children. And we're just going to slowly build the binary tree from the bottom up in this way. So we're going to keep doing that. And then we're going to add this new node we've created to the queue. So that way we're always picking the nodes that have the highest frequencies so that we have the shortest Huffman codes for the characters, the symbols that have the highest frequency. And then we're going to go ahead and remove that last node from the tree, and that's going to be our root node. The final step in preparing to encode and decode is to create the encoding map. The encoding map takes as an argument the binary tree, the Huffman tree, which in this case is just the root node, and we'll work from there. And we're going to create a dictionary we can use to encode from that tree. And to do that, we're just going to traverse the tree completely. So, and as we do, we're going to add the codes. Once we reach a leaf node, we'll add that code to our map, which is why we're passing it as an argument. So this is a private helper function to recursively move through the tree. And it's our base case for the recursive traversal is if we're at a leaf node. If the node is a leaf, then we're just going to add that code straight to our dictionary, our map, our encoding map. And if it's not, then we're going to recur down the left side of the tree, and we're going to recur down the right side of the tree, and we're going to update our code to have a 0 or a 1. Right here, we're not passing a code, which means it's going to be set with this default parameter to be an empty string. And then if we move down the left, we're going to add a 0, just like we saw in the PowerPoint. And if we recur down the right, then we'll add a 1, which will eventually get added to our encoding map once we reach a leaf node. And in that way, we build our encoding map and we just return it. Well, then we've got all our preparation done, and now we can encode and decode. Well, how does that work? For encoding, we take our text, whatever we want to encode, and then we take our encoding map as an argument, the one that we've created using these two functions here. It gets returned on line 71. We're going to take both of those and use it to encode the text. So our encoded string right here, normally these would be bits in a file, but for the purposes of illustration and for the purposes of our test here, we've got it as a string. And that string just starts out as empty. And then we're going to loop through each character in the text and then access our map to see what its Huffman code is and translate it into its encoded form and add that to the string. And then we'll keep looping through the text. And we just return whatever that encoded string is. And because there's only one loop here, a for each loop, and we're moving through each character of the text, this operation is O of n. As the more characters you add, the longer it will take in a linear fashion because there's one more character to do in this for loop. Well, decoding is also linear time complexity, and we can see that here. We've got the text coming in along with the tree. This is the root node of our tree, and so we're going to call that n, so that way we can reset back to the top of the tree. So we're going to loop through all of the encoded characters. Just as I said, O of n, right? For each character in this encoded string, we're going to loop through this one time. So if the character is a 0, then we're going to move down the left branch of the tree. This is the left node that we set up here. We can set this left node as this child, right? Well, we're going to move down that left node, and if for some reason that node doesn't exist, then decompression failed, we're going to throw an error. But we're going to move our node, the node we're currently sitting at, to that left right here. And if it's a 1, then we'll move down the right, and we're going to, and then we'll check once we've moved to see, have I arrived at a leaf node? If this node is a leaf node, then I want to know what letter it is, and I'm going to add it to my decoded string, which is what's happening on this line. And if we are at a leaf node, then set me back to the top of the tree so we can continue decompression with the next 0 or 1 in the sequence. And then this just repeats. And so sometimes you'll go 0 or you'll go 1, and then we won't be at a leaf node. And if that's the case, then we'll just loop through the next character and go 0 or 1 and loop through the next character. The beauty of Huffman codes is that they're called prefix codes, meaning none of the codes repeat within another code, meaning this is always guaranteed to be unique. I will always uniquely arrive at a leaf node, and we just return whatever we decoded. The beauty of Huffman encoding is that we can compress text, and the encoding and decoding operations happen in a linear time fashion, which is impressive and useful.